Today, we are going to be talking about motion. We're going to be finishing up what we started learning about motion. Velocity versus acceleration. This is where we left off from last time. One of the most important misconceptions that people will have this semester is the difference between velocity and acceleration. I keep harping on this because it is such an important point. Velocity is the rate of change of position. It's how quickly you're changing your position. Acceleration is how quickly you're changing your velocity. So it's something that you need to get accustomed to when dealing with motion. We need to understand the difference between velocity and acceleration. So the higher the velocity, the faster the position changes. The greater the acceleration, the faster the velocity changes. It is an absolutely vital thing to remember as we go through this. Does anyone have any questions? Actually, no. I'm going to skip ahead to this slide. Let's go over these concept questions. I want you to think about velocity and acceleration in these cases. Imagine driving on a highway. What is your velocity and what is your acceleration? Now, obviously, you don't know exactly what the velocity is, but can you tell me if it's positive or negative or zero? Is your acceleration positive, negative, or zero? Figure that out and just tell me in chat what you think. You can send it to everyone as well. And let's do that for each one of these. What if you are speeding up to pass someone? Is your velocity positive or negative or zero? Is your acceleration positive or negative or zero? Slowing down because the next traffic light in front of you is red. Well, what's your velocity? Positive, negative, zero. What's your acceleration? Positive, negative, zero. Backing out of a parking space. What's your velocity? What's your acceleration? And what is the velocity and acceleration of your car the moment that the traffic light turns green, assuming you have very good reaction times? Let's talk about each of these in turn. Driving on a highway. Oh yeah, I've got several answers right there. Fantastic. Driving on a highway, that's going to give you a positive velocity, assuming that forward is positive. I actually never said if forward was positive or negative. Well, actually, I did last time. I said we'll always treat forward as being positive, or almost always treat forward as being positive. Presumably, you're driving forward on a highway. I would not really like it if I saw someone driving in reverse on the highway. That would be bad. So presumably your velocity is positive on the highway. If you're just driving at a constant velocity on that highway, then your acceleration is zero. No acceleration if you're not changing your velocity. If you're going at a continuous 75 miles per hour on the highway, zero acceleration, positive velocity. Speeding up to pass someone. I saw some good comments in chat about that too. If you're passing someone, your acceleration should be positive because you're speeding up. Your velocity is still presumably positive. I'm again hoping that you're not driving down this highway going in reverse, but also speeding up in reverse. That would be even worse. So we'll assume that your velocity is positive and your acceleration is positive. Excellent. What about slowing down because the next traffic light is red? Oh, we've got some good answers for that one too. If you are slowing down because the next traffic light is red, your velocity is positive. You're still driving forward, but you have a negative acceleration. You can have a positive velocity, meaning I'm going forward, but a negative acceleration. that means that you're slowing down. A negative acceleration implies that you're losing speed, which is totally okay. This one right here, slowing down because the next traffic light is red, that ends up breaking so many people's brains on a test. A lot of people are very uncomfortable with the idea that you can have a positive velocity and a negative acceleration, but that's totally fine. It just means that you're slowing down. We'll talk about this in depth soon, but if you throw an object up into the air, so you have a ball and you throw it straight up into the air, well, it starts off with a positive velocity because it's going up, but it's losing that velocity. It slows down. If you take an object and throw it up into the air, you'll see that it slows down and eventually stops. And so it has a positive velocity and a negative acceleration. If you're backing out of a parking space, I saw some good comments in chat about this one too. You can have a negative velocity. You're backing out of the parking space, negative velocity, and the acceleration depends on, did you just start backing out? Well, if you just started, you're probably having to accelerate a little bit. If you're going backwards a little bit faster and faster because you just started backing out, then you probably have a negative velocity. Well, you definitely have a negative velocity, and you probably have a negative acceleration because your velocity is getting more negative. Now, if you're going at a constant speed, backing out of that parking space, which for most of the time when you're backing out of a parking space, you're going at a constant speed, your acceleration will be 0. But if you're backing out of the parking space and slowing down, you can have a negative velocity and a positive acceleration. You're getting less negative. If you're going backwards, but going backwards slower and slower, you're getting less negative. And if you're getting less negative in your velocity, that means that you have to have a positive acceleration. If you're backing out of that parking space, and let's say instead of thinking about cars, let's think about it on other terms. Let's just say that you're going backwards, you're walking backwards. It doesn't even really matter in what kind of vehicle. Let's just say you're walking backwards. Well, if you're walking backwards at a constant speed, then you've got no acceleration. I think that's pretty comfortable for most people. If you're walking backwards, but you're speeding up, you're going backwards faster and faster, and you look at your GPS and it tells you your velocity. Now your GPS, let's say that your GPS on your phone is smart enough to understand what direction you're going and what the directions mean. So maybe it understands that you're going in a negative velocity. You're going south or something like that. So that when you start running backwards faster and faster, it says, oh, every second you're going south more quickly. That means that you have to be accelerating south. But the way that we define direction is south is negative. So your GPS would say you have a negative acceleration in the y direction, I suppose, going backwards faster and faster. And if you're going back slower and slower, you're going back at some speed, but maybe there's a wall behind you and you don't want to run backwards into a wall because that would not be comfortable. Then you have to add to your velocity to get yourself out of the debt. You can think about a negative velocity as if it's a debt. So you need to pay off that debt by increasing your velocity, but you're increasing it in the positive direction. You have a negative velocity, but if you increase it in the positive direction, you get less negative. You're paying off that velocity debt with a positive acceleration. Oh, good comment in chat. It's because velocity is directional in a way, positive or negative on a graph, but your speed is still an absolute value that your acceleration can increase or decrease. Yeah, speed is a scalar, so it doesn't care what direction you're going in. Acceleration is always a vector, so we should be careful not to mix speed and acceleration because you should never really mix vectors and scalars. There is no scalar version of acceleration, which just adds to the confusion, unfortunately. But in this class, we are going to be talking about velocity. So, and velocity and acceleration, the vectors. So it becomes less important to be, you know, we should always be careful about that, but we're going to be careful by always just talking about velocity as much as possible. Fantastic. Okay, next one. Your car, the moment the traffic light turns green. Well, this is the one that I think also is going to make people a little bit confused. Your velocity the moment the traffic light turns green should be 0. Like if you're sitting there at a red light, the moment that the traffic light turns green, your velocity should still be 0. But, oh, as Nicholas in chat is saying, you've got a 0 velocity but a positive acceleration, because as soon as the light turns green, as long as you're paying attention, you hit the gas and you start accelerating. And so that moment, if you have fantastic reaction times, your velocity can be 0, but you can have a positive acceleration. Just think about this. A lot of people are uncomfortable with the idea of having 0 velocity and positive acceleration, because they say, well, you can't have that because acceleration must mean you're changing your velocity. So how can you have no velocity but be changing your velocity? Well, imagine an object that's going to start accelerating. There has to be a moment when it goes from 0 velocity to positive velocity. And in that moment, it starts off at 0 velocity, but then you give it a positive acceleration to make it start moving. If you could not have a positive acceleration and a 0 velocity, then nothing would ever be allowed to move. If a 0 velocity implied a 0 acceleration, then you could never change anything's velocity because you could never change the, because you can never have an acceleration. Therefore, you have to be able to have 0 velocity and an acceleration just to make something move originally. Give you this slide with all the answers so that you can check that out. Let's talk a little bit about calculus. I give you what we've already talked about, the derivative of velocity with respect to time, which is the rate of change of velocity, is the acceleration. The rate of change of position, the derivative of position with respect to time, is the velocity. These are slopes. These are slopes that you have to think about. The slope of velocity is acceleration. The slope of position is velocity. If you reverse that, and I know that most of you have not taken Calculus 2 yet, you'll see that to reverse that, you take the integral instead. Derivatives are all about slopes. If you can graph something and then look at the slope of that line at any particular point, then you're doing calculus. You're doing derivatives. If you draw a function, draw a line on a graph, and you think about the area under that curve, you count the area under the curve, then you're doing integration. The integral of your velocity with respect to time is equal to your change in position. The integral of your acceleration with respect to time is your change in velocity. Let's do this. Let's make these graphs. We need to make a graph, or from this graph of the position, we need to make a graph of the velocity. We can assume y is in meters. This y-axis is the position in meters, and the x-axis is the time in seconds. Let me redraw what we had in the previous slide. Went something like, this is the position, and we started off down here with our position, went up, went back down there, and then just stayed at a particular place like that. If we start here at t equals 0, this is time in seconds, we start here. The slope here is positive. The position is negative. This is like -2 meters or something like that. How about let's think of this in terms of how high up something is. Usually we have that as y instead of x, so I can just relabel that as y. I don't really care. All this stuff works just the same, whether it's x or y or z. So let's say that something starts off 2 meters below some point. Maybe that some point is the top of a table. Maybe there's a table somewhere, and we're going to define the top of the table, just this table that I'm on, to be 0. And so this might be something starting off at the floor. That'd be a very tall table if it's 2 meters high, but go with me on that. Something starting off on the floor. Well, as it goes, as time increases, eventually it comes to the same level as the table. When it gets to x equals 0, then that's the same level as the table. It had to have a positive velocity to get up to the table, and the slope here in this region is definitely a positive slope. But as time goes on and the object gets higher and higher and higher, it's getting higher and higher up, that slope decreases, meaning the velocity decreases. Eventually, the slope gets to 0. Here, at that point, the slope gets to 0. That means that the velocity must be 0 at this point. At that point right there, the velocity must be 0 because the slope is 0. And then the slope goes negative. The slope is negative, 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 negative. And even after it passes the table again, remember this is the surface of the table, it's still a negative slope like that. And then we get to this point and we have a slope of 0 again. No slope in this segment there. So now we can draw the velocity curve. As we said at the beginning, the velocity is positive. But as time goes on, it gets less positive. The slope goes from a very large slope to a lower and lower and lower and lower slope, like that, less and less slope. And then eventually the slope goes to 0. So I'm actually going to mark this point. That's the point where the slope goes to 0. I'm going to use my pencil for this and say that, what's going on with the pencil is the velocity. So the velocity will start at some point, I don't know where, let's say there. And the velocity will decline and decline and decline because the slope of this line is decreasing. Then the value of the velocity must also be decreasing. Here, the slope of the x position is 0. Slope is 0. Therefore, the velocity must be 0 at that time. At whatever time this represents, because this is the time axis, at that time, the velocity must be 0. And then the velocity continues to decline as this continues to get more and more negative. And then at some point, right here, the velocity goes from going very negative, slope is very, very negative right here, to a slope of 0. And that means that this would have to jump up like this and have a 0 velocity at that point. This line marked in pencil, that's the velocity. That's the velocity. I'll just write the velocity next to it so that we can see that. And I'm not really caring about what any of the numbers mean. So we can do this just very quickly and visually. Why did the velocity not start increasing there like that? We have to, the speed, if we were graphing the speed, you'd be totally correct that the speed should start going back up at that point. But we're not graphing the speed, we're graphing the velocity where direction matters. What I actually graphed is kind of like when you throw something into the air, it goes up. Imagine this just being the graph of the position of something that I've thrown into the air. And I throw it from the floor, and the floor is 2 meters below wherever I'm starting at the 0 point. Say, actually, this makes more sense. Say that I'm 2 meters tall, and I'm counting the top of my head as being the 0 point, but I somehow throw something up from the floor. Maybe I'm kicking something up from the floor. Well, it's going up, going up, going up, but it's slowing down as it goes up. So the velocity gets less and less and less. When it reaches its highest point, it stops. It has to stop at some point. If it doesn't stop, it's just going to keep going up forever. But then it starts falling down. And if it's falling down, it has a negative velocity. And eventually it hits the floor. Notice that the velocity goes to 0 the moment it gets back to -2 meters, which is kind of, I guess I'm saying that's where the floor is. So it hits the floor, and then it goes to 0 velocity there. So a negative velocity implies that it's going down instead of going up. So remember, that's our velocity graph. I'm going to change this to an acceleration graph now. I'm going to use this to find the acceleration graph. So now, instead of on this, I originally had this as the position graph. Now, I'm going to have this as the velocity graph. Now I'm graphing the velocity versus time. And so I'm just going to copy what I had before. Just look like this. That's just what I had before for the velocity. I'm not going to bother drawing in the position because that just makes it confusing. Let's use this to figure out what the acceleration graph would be. Well, okay, we can just go kind of across and say, what's the slope at every position? Let's look at the slope initially. Well, the slope is that. It's negative. We've got a negative slope initially. And then let's go here, let's say. Okay, I've got it's the exact same negative slope. And now let's go down here. Oh, I've got the exact same negative slope. I've got the same negative slope this entire time. That means that I have a constant negative value for the acceleration. I don't know exactly where to draw that, but let's just say it's here. This whole time, I've got a negative slope to my velocity. That means that the value of my acceleration has to be negative the entire time. Then I get this weird spike where I've got like a positive infinite slope, which, okay, that actually does something weird. You've got a crazy weird spike, but ignore that. It doesn't even matter because it takes place over an infinitely tiny amount of time. And then you've got 0 slope and therefore 0 acceleration there, like that. Because this has a constant negative slope, the velocity has a constant negative slope, the acceleration will be a constant negative value. In fact, if this is the example of throwing something into the air and then letting it come down, then this would be negative 9.8 meters per second squared. We'll talk about that probably later on today, why that is, but that's the acceleration due to gravity. Here is the position graph. Here is my nice professional velocity graph, just exactly what we drew together. And here's the acceleration graph in green. Now, obviously, this makes it very, very confusing having all these things all on top of each other. I don't really recommend that you ever do this, that you have so many graphs all being piled on together. If I ever ask you a question like this on a test, I'll give you separate graphs to look at and not pile them all onto one thing. We can verify that any of this is actually reasonable. I give you the position function from 0 to 10 seconds and the position function at a time greater than 10 seconds. If you take the derivative of the position function that I used to graph what I had on the previous slide, it gives you this velocity. So you see here, the position function is a quadratic. It's a polynomial with a t squared and a t and a constant. And so that means that you have this parabolic shape there. And in fact, it has a negative squared component. So you get the downward facing parabola there. You take the derivative of that and you get, okay, derivative of this, hopefully you've all had enough calculus to remember that. Derivative of this, the 2 comes down, it becomes negative 0.4t, negative 0.4t. This goes away, plus the t goes away, so it's plus 2. So 2 minus 0.4t. Well, this is just y equals mx plus b. You've got a constant slope and an initial point there, which is exactly what you find in that purple line. Constant slope, but it starts at positive 2 in this graph. Starts at positive 2 in that graph. And then you take the derivative of this. This is the time greater than 10, which is over here where everything is flat. That just gets you a velocity of 0. You take the derivatives of these. Well, the derivative of this, the 2 goes away, the t goes away. You get negative 0.4, just like that. An acceleration of 0 after t equals 10, which negative 0.4 in green, and then 0 after that. I offset it a little bit so that you can actually see it. We can do this with other kinds of graphs as well. This is the graph of a velocity. You start off at some positive velocity, 5 meters per second. And then think about this. What is happening in this stage? You are going from a constant speed and then slowing down. Learn to start interpreting graphs this way. I go to constant speed, and then I start slowing down, and then I've stopped, and I just stay stopped for the rest of the time. Yeah, deceleration. This period right here, from 5 seconds to 10 seconds, is a deceleration, or you can say that the acceleration is negative. Those are completely consistent with each other. Decelerating and acceleration is negative, those mean the same thing. So we can use them interchangeably. I'm usually going to say things probably more like acceleration is negative when we're talking more mathematically, and I'll say things like deceleration when we're talking more conceptually. So each has a good place. The velocity is decreasing over this time, over the 5 to 10 seconds. And you look at the first 5 seconds there, you've got a constant slope, and so no acceleration, meaning no change in velocity. So the acceleration will be 0 over the first 5 seconds. And then you've got a negative acceleration or a deceleration for the next 5 seconds. In fact, I made this so that it's decelerating by 1 meter per second every second that elapses. So it should be a deceleration of 1 meters per second squared, or an acceleration of negative 1 meters per second squared. See how confusing that can get? Going back and forth between deceleration and a negative acceleration. We do need to be careful when we talk about that, just to be consistent with what we actually mean. And then over here, we have stopped. We're not changing our velocity at all, and so we have 0 acceleration again. And so I give you that in green here, going like that. We can find the position after 5 seconds, after 10 seconds, and after 15 seconds. Oh, can we find the position? We can find the position after 5 seconds, 10 seconds, and 15 seconds looking at this graph. Remember, on a previous slide, I said that the position, the change in position of an object is equal to the integral of the velocity with respect to time. And if you've taken calculus 2, I suppose, you know that the integral of a function is equal to the area under the curve, or it's related to the area under a curve. Now, it doesn't matter if you have not taken calculus 2 yet or not, because we can just look at this and say, okay, what is the area under the curve? Let's go to this, find the position after 5 seconds. That's just going to be the area. Actually, can we find just the position? No. What we need to be looking for is the change in position. Remember, I had that delta x. So we can figure out how much the position changed from t equals 0 here on the y-axis up to the 5 seconds line. And that's just going to be 5 seconds times 5 meters per second. The area under this curve is just the length of this, which is 5 seconds, times the length of this, which is 5 meters per second. So 5 seconds times 5 meters per second, well, the seconds are going to cancel out with each other, and you're just going to have 25 meters, which is the change in position that you'd have if you went 5 meters per second for 5 seconds. You would change your position by 25 meters per second. Or sorry, you change your position by 25 meters, excuse me. Over this period of deceleration or negative acceleration, you can still find your change in position from 5 seconds to 10 seconds. That's still going to be the area under the curve, which is going to be, well, this is a triangle, so it's 1/2 times the height times the base. That's going to be 1/2 of 25, or 12.5. And then the area under the curve for the rest of it is 0. Because 10 to 15, there's no area under the curve. Also, you're not moving. Your velocity is 0. Therefore, if your velocity is 0, you'd expect your change in position to also be 0 over that period of time. And then if I ask you, okay, 5 seconds, 10 seconds, 15 seconds, well, the 5 seconds is just going to be the 25 from this block. The 10 seconds will be the 25 there, plus the 12.5 there, 37.5. And then 15 seconds should still be 37.5 meters. If that's going from 0 to 5, then 0 to 10, then 0 to 15. So give you those answers there. And I give you the equations that I used to create this, this graph. So you can try this again on your own if you wish. I have this big section here. It's a whole bunch of slides. And I've got the work here